Welcome to the virtual presentation of X bridges, designing tunable bridges to enrich 3D printed objects, deformation, and stiffness. I'm Jiajie Li, and I will be presenting our team from International Design Institute of Zhejiang University. Bridges are unique structures in fused deposition modeling, FDM printing, that make rigid prints flexible but not fully explored. X bridges is a design tool to allow novice users to design tunable bridges that can enrich 3D prints with multiple behaviors of tunable flexibilities. Compared to existing method, we adapt the advantages of metamaterial, fabric manufacture, and parametric remodeling tool for quick prototyping without post-process. Our parametric design tool creates tunable stiffness of connections, including stable, elastic, and loose, which allow users to on-demand modify with the final artifacts. We should start from FDM printing to explain the mechanism of X bridges. In FDM printing, the certain toughness of filaments enables it to resist gravity at a short distance, which is so-called bridges. We take advantages of extra compliance of it to perform both flexible and rigid with one material. Our further research designed it as connections for solid sheets, origami, blocks, torsions, and stretchable structures. I will take the wheel again as an example to introduce our workflow. Firstly, virtual models is imported and divided into multiple parts. The gaps in between enable deformations. Users can adjust reform position, deformation angle, and the gaps amount to get their ideal result. We conducted a series of tests in order to determine the optimal parameter and their interplay for X bridges. Among all the parameters, bridge densities, extrusion flow rate, and print speed have dominant effect for physical properties of bridges. We also use some quantitative experiment to distinguish plastic deformation from elastic deformation, together with extrusion control algorithm to calculate the extra filaments for relative extrude mode for further G-code generation. The experiment results were integrated with X bridge design tool. With options of stiffness, the G-code would be generated accordingly with different settings. Here are three results. The first one is stable. With minimized bridge's length and the largest extrusion, the reformed tail keeps its shape after being manipulated. With medium extrusion, longer bridges would be elastic in a certain range, which would keep the objects bouncing back just like a spring. With the minimum extrusion parameter of 70% and a minimum printing speed, thin and long bridges are no longer stiff enough to resist the gravity. Besides the tunable stiffness, we develop deformation structures including bend, stretch, compress, and twist. Though some of them seem similar to existing structures, they are consisted of flexible bridges and rigid parts, so all deformation only occur on bridges, which could be well controlled with printing parameters I've mentioned before. We also made some samples to explore the design spaces. For developable surfaces like origami, here we leverage tessellations of mural folding and curved folding. And also we leverage a vase with non-developable surfaces and stable bridges, so it could stay the shape after manually deformed. By replacing part of a metamaterial cube with different density of bridges, it performed pretty different with same pressing force of 10 Newton. Though these tiny bridges seems vulnerable, our fatigue limit test shows that it could be deformed more than 7,000 times in 4 hours. Then I will show some applications to indicate what we can really do with X bridges. X-Bridges allows us to make modification and fabricate everyday products in different scales. For instance, a hanger. We're replacing the shoulder and the pants part with stable stretching structure, so it could fit both adults and children's clothes. With loose bridges transferring motions and rigid bridges connecting bars as crosses, we also present a fully functional crocodile toy that can extend and retract by trigger. In next example, we showcase two bunny ears with different parameters. The first stable pair is only deformable by extra manual forces, while the second loose one would swing freely with the wearer's motion of jumping, dancing, or even simply walking. Rather than regular even extrusion, we modified the G-code file to increase extrusion flow linearly from 80% to 160%, which gives the button a resistant gradient on the layer for every segment. In conclusion, shape changing, physical property changing, and model reforming features enable our design tool to generate multi-form and multi-use applications. We look forward to applying our method to future sustainable fabrication. Thank you for watching.